Okay, so I'm going to talk about quantified Boolean formula. So I will explain the motivation and as well as give you the complete proof of the main result. So that way you will at least get some technique out of this paper. So just to give you some historical perspective, and if you look at the satisfiability problem, many types of satisfiability have been studied, and among them are the most well-studied are the k-SAT, CNF-SAT, maybe bounded depth circuits, and formulas. Okay. So if you look at the kind of results people have obtained, k-CNF, which is one of the most well-studied, so the savings in the exponent, you already know what I mean by savings in the exponent. You have heard many talks that talk about exact algorithms and parameterization. So we are measuring complexity in terms of 2 to the n times some constant in the exponent, and that constant is 1 minus 1 over theta over k for k-CNF, and this seems to be the best possible bound people are able to obtain so far. Okay, and we also call 1 over theta of k the savings we can obtain from these algorithms, so over exhaustive search. Okay. From now onwards, I will talk about savings or non-trivial savings and how the savings approaches 0 as k goes to infinity or as some other parameter of the circuit grows. Okay. So the second model is CNF-SAT, and Schuller has come up with a very nice idea whereby he could show that that Cn class CNF is essentially the same as log C CNF. So there's a kind of duality which we made more precise subsequent to that of Schuller's work. So basically Cn clauses in a CNF where the clause has no width restriction is kind of dual to log C width CNF. Okay. So with the duality you can see the savings you can obtain is 1 minus 1 over theta of log C. Okay. So more recently, actually last year in IPEC, we with our student Chris Calabria, Russell and I presented this upper bound on depth D circuits with Cn gates, and the upper bound on the savings is horrible. So it's a double exponential function of the parameters C to the D to the C to the 2 to the D minus 2. Okay. So we were happy at the time that we got somewhere, we were able to somehow conquer the depth, can extend the k-CNF results or k-CNF upper bounds to larger depths. But in retrospect, we realized, no, it's not just important to get some savings, but also try to get the best possible for basic Boolean circuits. So we were able to show that switching lemma is sufficient to get the same kind of bounds that I showed here. Okay. Not only for k-CNF and CNF, but for depth D circuits in general. That talk will be in the future, hopefully. Okay. More recently, Rahul Santanam has shown that for Cn size formulas with no depth restriction, so this is a nice result in the sense there is no depth restriction on this class of formulas, and he's able to show a savings of the type 1 over poly C. I think poly is like C square or C cubed, something like that. Okay. So this is what's known about the plain Boolean models and the satisfiability upper bounds, and so now let's look at somewhat more complicated complexity model, complicated circuit models or formulas. So these are the quantified k-CNF. So basically, quantified k-CNF means you have a formula in the pre-next form. That means all the quantifiers come in the beginning, followed by a k-CNF. So you have Q1, X1. So you have, for each block of variables, there is a quantifier, and the quantifiers alternate, and followed by a k-CNF. So, okay. So let's look at the complexity of this one, and this problem has been looked at clearly. Okay, when you don't view when you don't care about the complexity parameter n, which is the number of quantified variables, this problem is a piecewise complete problem. Okay. So, but on the other hand, when you restrict, when you kind of focus on the complexity parameter n, which is the number of variables, as well as restrict the width, perhaps interesting results could be obtained. So, for example, when k is 2, so since 1979 itself, people have observed that this problem can be, so this problem can be decided, the quantified 2CNF problem can be decided in polynomial time. So this is not too complicated, but on the other hand, it's not a trivial algorithm, and it's a linear time algorithm. Okay. But on the other hand, so that's one result we know, but on the other hand, if you go from 2 to somewhat higher number, we don't know much. But what we know is that if you take a more powerful quantified circuit model, so you have a quantification followed by an arbitrary Boolean circuit, okay? So then clearly one can solve it in 2 to the n times poly of the size of the circuit, okay, by doing an AND OR tree and evaluating that AND OR tree. And since the number of variables or the number of quantified variables is the complexity parameter here, so we can solve it in 2 to the n times poly c. So we have these two extremes. We can do it in linear time when k is 2, and when the formula is replaced with a more powerful and arbitrary circuit of poly size, we can solve it in 2 to the n times. Okay. What about the cases in between? Okay. So that's exactly the problem we are looking at in this paper, and what happens when k is 3 or 4 or whatever. Okay. So what's the motivation for looking at? Okay. So this looks like a small industry, small scale industry. You look at your favorite formula or circuit model and ask for the satisfiability algorithms for that model. So this is simply a game. We can produce more papers by looking at more models or by inventing more models. Okay, is there a larger reason beyond this simple game of having fun? Okay. So there's a deeper motivation for studying these various models, and so let me give you the philosophy in 2 or 3 sentences. And so there is this intuition that the larger the expressive power of the underlying computational model or the circuit or formula, the more difficult it may be to find the satisfying assignment. Okay. So therefore, what would be interesting is that what is the smallest or the least expressive formula or circuit model for which we cannot hope to obtain any non-trivial savings for the satisfiability algorithm. So that means, so you want to approach from below, so start with simpler models like k-CNF, okay, and keep increasing the complexity of these models until you come to a point, or until you come to the frontier in this space of models where you cannot expect to get any kind of savings, over exhaustive search. So not only that, so that will kind of tell you, so that will give you some idea about the powers of the satisfiability algorithms. Not only that, you want to understand how, as the circuit or the formula parameters change, like the depth or k or the size, they change, how the savings diminishes to 0. That's a kind of functional relationship you want to understand. For example, for k-CNF, the savings vanishes as k goes to infinity as 1 in k. Okay, so you want to understand that precisely, okay, so as precisely as possible. So that's a larger motivation. If you can achieve this even under a suitable hypothesis, so this enterprise will lead to plausible exponential time lower bounds for various combinatorial problems. For example, you can simulate linear size circuits by so you can reduce linear size circuits to various combinatorial problems without blowing up the complexity parameter. So that will help you establish kind of relationships. Ultimately, you might be able to derive lower bounds on the exponents for various combinatorial problems, assuming something like ETH. So this is a larger enterprise. We still don't fully see the picture there, but right now the goal is to approach from below and to understand it as well as possible. So that's the context in which we are looking at this quantified CNF. So, okay, so before I go through the main result, I want to give you some definitions, very simple definitions. So let phi be a class of instances. For example, phi could be the class of k-CNFs, okay, or phi could be the class of quantified formulas and so on and so forth. So what we are defining is that this constant s of phi, which is the best constant such that you have a 2 to the s of phi times an algorithm for solving this one. For now, assume it's a deterministic algorithm. Okay. So with this, we can define a series of constants. We want to understand how these constants behave and what are the relationships among these constants. Okay, we know for k-CNF, we know that s of k is less or equal to 1 minus 1 over k. So the upper bounds establish that you can do at least 1 minus 1 over k and perhaps better. Okay. So just instantiating this for various types of phi. So we have s of k, which is the familiar one, and the limit of limit of this s of k is s infinity. Okay. I changed the notation from subscript to functional, but so you understand what I mean. And so with this notation, we can state exponential time hypothesis as s sub 3 is bounded away from 0. And strong exponential time hypothesis is that s infinity equals 1. So this is a very strong assumption. Partial justification comes from the fact that the best known algorithms for k-CNF behave like 1 minus 1 over k. So therefore, as k goes to infinity, so the constant tends to 1. So that's a weak justification, but so we don't know anything better than that. Okay, now let's go into quantified. With those definitions, let's go into quantified formulas. And so let's look at somewhat, so rather than looking at the arbitrarily quantified formulas, so you want to, so to make some progress, you want to look at bounded number of quantified blocks. So for that reason, so let's define pi sub I k sat and sigma sub I k sat are those problems where the first quantified block starts with universal or existential, as the case may be, and they alternate, followed by a k-CNF. And the total number of variables is n. Okay. So similarly, we can define the complexity of solving these problems, and s of pi sub I k-CNF or k-sat and s of sigma sub I k-sat are the best possible constants for solving these problems. Clearly, we know these constants are less than or equal to 1. The question is that is the constant strictly less than 1? So that's at least the minimally interesting question, or the basic question to ask first. So notice a couple of things. These quantifier blocks are, so when the quantifier block is existential, and if there is only one quantifier block, that's the same thing as satisfiability problem. Okay, you have just existential quantification. But on the other hand, if you take sigma 2, that means you have existential quantifiers followed by universal quantifiers followed by a k-CNF. That turns out to be the same thing as sigma 1, or that turns out to be the same thing as a polynomial, simply existential quantification. So therefore, both of them are equivalent to the k-CNF problem. So the point is that when you have a k-CNF and if you have universal quantification so over the variables, and as long as you have a clause where every literal or variable is universally quantified, it's always possible to set that clause to 0 and make the whole formula 0. So therefore, for a universally quantified k-CNF not to be false, so you got to have a trivial formula. So for that reason, sigma 2 k-sat is solvable, same thing as k-CNF. Okay. So, but on the other hand, so the same reason says pi 1 k-sat, that means you only have universal quantification followed by k-sat, that actually is solvable in a polynomial time. So the reason I'm kind of mentioning all these things is that the first interesting case comes when you consider pi 2 k-sat. So we are looking at formulas of the type for all bunch of variables, universal quantified variables followed by a series of existentially quantified variables followed by a k-CNF. So what's the complexity of this? Okay, so that's the precise question we are going to look at, and what can we say about the corresponding exponent? Okay, let me quickly refer you to some of the previous work. Ryan Williams has looked at this problem long time ago, and so he looked at a slightly more general problem, dk-CSP. So where each variable takes d values and width of each clause is k, and he also specialized it to the case d equals 2. That's when you get k-CNF. He looked at arbitrarily quantified formulas that are of the type d2-CNF or d2-CSP. Okay. So the important difference is that he parameterized the problem by the number of clauses. Several years ago, people have been spending time on trying to obtain bounds based on the limited number of clauses. So that's important. So that means the larger the number of clauses, so the worse. So the complexity parameter goes up. So let me quickly flash all the results. And so these are some of the bounds. If you look at a typical result, so let me look at the second result. It is 2 to the 0.536 times Cn, time and space upper bound for a quantified 2-CSP. Or if you want to have purely a Boolean case, then it is the 2-3-CSP, which is basically quantified 3-CNF, and the quantifiers are arbitrary. And he could solve it in time 2 to the 0.61 CN. Okay. And the point here is that each of these upper bounds will yield non-trivial savings compared to exhaustive search when the number of clauses is less than 2n. So that means these class of formulas he looked at are quite weak in terms of expressive power, but of course he was able to get something better than exhaustive search. So what we want to do is that we want to take the complexity parameter to be the number of variables rather than the number of clauses. That way we get somewhat stronger results. So that's what the precise question is. So anyone has a guess as to what this S sub pi 2 k sat will be? So less than 1, equal to 1? Or does anyone guess? So we were hoping that, since this is a k-CNF ultimately in the formula, and we only have 2 levels of quantifiers, and the simpler levels can always, the simpler versions before this level, they all can be solved easily or equivalent to k-CNF SAT problem. So we thought the complexity might grow up a little bit by going to the slightly, one more layer of quantifiers. So to our surprise, we found that this problem is kind of complete with respect to the k-CNF SAT problem. So that means S infinity, which is the limit of all the constants Sk, is less than or equal to this constant. So that means if you believe strong exponential time hypothesis, you cannot expect any non-trivial improvements over exhaustive search for this quantified, 2-level quantified CNF problem. So even when k equals 3. So even 3-CNF is hard once you quantify it pi sigma, or universal followed by existential. Okay. So that's a surprising result, and it also tells you why Ryan was not able to succeed beyond the results he was able to get. So that means had he succeeded with complexity parameter n, that would have yielded a much better algorithm for k-CNF where the exponent may not be depending on k. That would be an extremely surprising and very interesting result if that were to be the case. Okay, so this gives kind of evidence. Maybe things are kind of ordered for a particular purpose. Okay, so this is how the world falls out. Okay, so not only that, so that means the level. So if you look at the hierarchy of these quantified formulas with respect to the k, and when k equals 3 itself, it tops off. Okay, so if you look at the k-CNF, assuming ETH, we were able to show that k-CNF complexity keeps increasing infinitely often. But whereas for these quantified formulas, k equals 3 is already, so you achieve the constant might be 1. So you can't keep increasing. So that's one more way of looking at it. So conversely, if the strong exponential time, conversely, if you don't believe in strong exponential time hypothesis, this result can be viewed as a positive inducement for you to work on pi sigma formulas, pi sigma 3-CNF. So if you can obtain any non-trivial algorithm, that will improve all k-CNF. So either way, you can look at the result okay. So what I'm going to do, there are a few other results regarding quantified CNF. Most of them are, okay, the remaining results in the paper are upper bounds, but this is the Q-test result, and the technique we use is also very neat. I believe that there are many other applications for this technique. I want to give you the proof in detail, so I hope I can do it quickly. Okay. So it's only 4 or 5 slides. So that's the theorem we want to prove. So what's the outline? It's basically a sub-exponential time reduction. So I will show you the reduction in detail. So you will see the power of sub-exponential time Turing reductions. And you also see the need for them and the application of Sparsification Lemma. So these are the tools: Sparsification Lemma, sub-exponential time reductions, and a new neat technique. Okay. So the idea is that take the k-CNF, take the given k-CNF, and reduce it to an equivalent 3-CNF or 3-DNF actually, that is universally quantified, where you introduce a small number of new variables y. Okay, so that's the basic step. So take the CNF k-CNF where k is arbitrary, so reduce it to a universally quantified 3DNF by using small number of new variables, and the number of new variables turn out to be square root of the original number of variables, roughly. Okay. And so then we have the so let's assume we succeeded in doing it. Okay, this is not exactly how it happens. There's a Turing reduction. You will get many such formulas, but if you look at it, so one such reduction, the Turing reduction. So you will see. So the problem we want to solve is that whether there exists an x such that f of x is true. This is the satisfiability problem for k-CNF. So that is equivalent to, so there exists an x such that for all y, a particular DNF. Okay. Now we can so let me see. I did not push the negation inside. Okay. So there is a small mistake there. The phi in the second in the last term should be negated. So I I negated the formula appropriately to convert the 3DNF into 3CNF, brought the negation forward. So therefore you will get the last term is that, so no, it is not the case for all x there exists y a 3CNF. Okay, so there is a mistake there, and correct that one. And so therefore you can see that there is a kind of equivalence between the satisfaction problem and the negation of the pi 2 SAT problem or pi 2 3 SAT problem, provided we can do the first step well. So the key to the first step is that how do we take a k-CNF, reduce it to quantified 3CNF in an equivalent way? Okay, a quantified 3DNF. Okay, so the key idea is to sparsify the given k-CNF to begin with. So let me go through the sparsification lemma very quickly. So rather than reading that proof, so let me kind of apply the sparsification lemma to the case in hand and show you what results. Okay, so we start with our k-CNF, which is f of x, and sparsification lemma lets us rewrite this k-CNF as a sub-exponential union. So select some parameter epsilon, 2 to the epsilon n disjunction or union of formulas g sub I, okay, where each g sub I is a k-CNF, but of the size linear in the number of variables, and the linear and the constant factor only depends on k and epsilon. Okay, and of course the time for this reduction takes 2 to the epsilon n time. So the point here is that each of the gi has a much more manageable size, and we are going to use that to kind of convert into a quantified 3DNF. Okay, so reducing the size of the formula is the key for the success of this enterprise. Okay, so we are going to do a Turing reduction. So for each g sub I, we are going to execute the strategy so that I mentioned earlier. So, and from this constant, you see that the number of, okay, previously I said that the number of new variables, the y variables to be introduced is c times square root n, that c is going to be more precise. It's going to be some constant, okay, some absolute constant multiple of the size of the g sub I. Okay, fine. Okay, so now let's focus on a particular g sub I, and let's call it g without loss of generality. So we re-index them. And it's a linear size k-CNF, and it's a conjunction of clauses. So without loss of generality, assume that each clause is a disjunction of k literals, okay, and the first k literals. Okay. So now comes a couple of key ideas. Somehow we have to convert, by introducing new variables, we have to convert this particular. Okay, what we are going to do is that, so we are going to take each clause of the k-CNF, somehow convert into a DNF, okay, in such a way that that you can sum up over all the clauses, and then you by introducing new variables. So this is a step that I'm going to describe in the next 3 steps. Okay, so without telling you kind of what the motivation is, let me simply syntactically explain the transformation. For each clause, what I'm going to do is that I'm going to select a term of 2 variables by using the new variables y1 through whatever. So I'm going to select t sub I, okay, for this class c sub I, and create a disjunction or a DNF, a d sub I, which is expressed as simply x1 times t1 plus x2 times t1 or ti, and so on. Okay. So what's the property of this disjunction d sub I? Okay. So let's assume the clause is true. Somehow the variables xi are set such that the clause is true. Then d sub I is equal, okay, then d sub I is equivalent to t sub I. So one of the literals is going to be true since the clause is true. The corresponding term will be non-zero. And we don't care, okay, since each of the literals is multiplied by the same term, okay, if one of them is true, you get the contribution t sub I, and if none of them are true, you get the contribution 0. So that's the relation between c sub I and d sub I. Okay, good. Okay. So now comes the next step. So for each clause, we take a distinct term t sub I, which is the product of two y variables. So I will tell you how to obtain those terms and what properties these terms must satisfy. So now what's the overall DNF I'm going to obtain? So the overall DNF is, I'm going to take another DNF, 3 DNFs in terms of the y variables called t sub 0 plus the disjunction of d sub I that I obtained previously. So each d sub I kind of encodes a clause. Okay. So let's now reason about this phi of xy. This is a 3 DNF. So let's assume the corresponding CNF is true. That each clause must be true. That means each clause has one literal which is true, and that true literal will produce the corresponding term t sub I. So therefore, when the k-CNF is true, this phi will be equivalent to t0 plus t1 plus t2, so on. That's going to be a 3 DNF. It actually is a 3 DNF where some terms have width 3. These are the terms in t sub 0. The remaining terms t sub I for I greater than or equal to 1, they have width 2. Okay. So far, I hope it's clear. So the point is that, okay, when the k-CNF is true, you get the full 3 DNF t0 basically all the way to the final term. Okay, when the k-CNF is false, that means one of the clauses is false. That means the corresponding t sub I will be missing from this expression phi. So depending on whether k-CNF is true or false, so you get a full DNF or a slightly reduced DNF. So that gives us an idea what is the requirement we want to satisfy. So we want to select t sub 0 and t sub I in such a way the corresponding DNF, which is the sum of those terms, is a minimal tautology. So what exactly is a minimal tautology? So this is a tautology in the variables y. Remember, t0s do not contain the variables x. Okay, when you write them as d sub I, that's how the variables x get attached to the terms t sub I. Okay, what's a minimal tautology? First of all, it should be a tautology. And if you drop any one term from the DNF, this is no longer a tautology. That's a minimal tautology. So select T0 and T1 and so on and so forth such that the corresponding DNF is a minimal tautology. And now let's go back to the previous thing. So that means when the k-CNF is true, the phi will be a minimal tautology. Okay. So we can express the fact that k-CNF is true, saying for all y, the corresponding 3 DNF is true. And when the k-CNF is false, this is no longer a minimal tautology, so the corresponding expression for all y, the 3 DNF is true is false. Okay. So we have expressed the truthfulness of the k or satisfaction of the k-CNF in terms of the this quantified Boolean formula. So the only job we are left with is that how do we construct such a minimal tautology? So what are the parameters of interest here? Why do we need c times square root and new variables? So what is the kind of, okay, so t sub 0 does not depend on the size of the k-CNF. Okay. The terms, okay, we need one term ti for each clause of the k-CNF. Since the k-CNF has constant times and many clauses, we need that many terms. We need to produce that many terms. And you want to produce linearly many terms of width 2, TIs. for I greater than or equal to 1 by using as few variables as possible. So that's what the construction is. So let me quickly flash through the construction and then we'll be done. So I'm going to take auxiliary variables, approximately some constant multiple of square root n. And let's divide these variables into 4 groups. So u's, v's, w's, and z's. Primarily, we'll be focusing on u's and v's. W's and z's are necessary, but they are less important. So now I'm going to come up with a minimally unsatisfiable system of clauses rather than terms. Of course, by taking the complement, you get a minimal tautology. So let me express it in terms of CNF. It's equivalent in terms of tautology. So what I'm going to come up with is a system of clauses. So what exactly are the clauses? For each of the variables u and v, I'm going to say ui implies vj. So that's a clause. Okay? And then I say one of the u's must be true. Okay? And then I say one of the v's must be false. I claim, so you can verify it at your own leisure. So this is very obvious. So if you think for a minute, you will see this is a contradiction. And not only is this a contradiction, if you drop any one of those implications, this is no longer a contradiction. So this will be satisfiable. Therefore, take the negation of each of the clauses, so you get a 3DNF. And what's the number of the width 2 clauses here? The number of width 2 clauses is for all I and j, you have implications ui implies vj. And the number of, the number of u's, so u is about order square root n. The number of v's is order square root n. So you take the product of them, so you get order n such implications, or width 2 terms. Okay, so that's exactly what we need to handle our case. Of course, these long disjunctions you have, so with u's and v's, so u1 or u2 or all the way, those can be converted into 3 CNF clauses or 3 clauses by using these auxiliary variables w and z. And that will not change the minimal satisfaction property. Okay. So that's basically the proof. So now you put everything together. So let me just. So we have a sub-exponential reduction, a Turing reduction, and you kind of look at all. So you account for all the time you spent. So notice we increase the number of variables from n to n plus order square root n. So therefore, we are solving the pi to 3 sat problem on a slightly larger number of variables. But then it is little of 1 when looked at as a ratio. So that's why you get the term 1 plus little of n. And then the reduction takes, the Turing reduction generates 2 to the epsilon and many subproblems. So for each subproblem, so you have to solve this, so do this reduction and solve it. So therefore, you have these various epsilon terms that are getting added up. But the fact is that Sparsification Lemma lets us select epsilon to be arbitrarily small. So that is something within our control. That's where the power of Sparsification Lemma comes into play. Okay. And that concludes the proof. Questions?
No questions? Okay, let's thank Mohan again. We come to the last talk of IPAC. Nina Taslerman is going to talk about the exponential time complexity of computing probability that a graph is connected.
Yes, can you hear me? Yeah, okay. So this is joint work with my supervisor, Tore Husfeldt. And I also talked a little bit about this on Dagstol a couple of weeks ago. So some of you have already heard this. So what do I mean by the title here? What do we mean by the probability of a graph being connected? Well, consider the following situation. You have a communication network of some sort, for example, a mobile phone network or a road network, where every connection or edge has some probability p of failing. So this happens often in everyday life, right? And then we ask, under these constraints, what are the probability that the graph stays connected? Now, for this certain pentagon here, I give as an example, there are two situations that this graph can be connected. Either none of the edges fail, or exactly one of the edges fail. And the probability that none of the edges fails is 1 minus the failure probability raised to the power 5 in this case. And the probability that exactly one edge fails is p times 1 minus p to the 4. Okay. And the latter situation can, of course, occur in 5 equivalent ways. So in total, we get this expression here for the total probability that the pentagon is connected. And this quantity here we refer to as the reliability of the input graph, given failure probability p. And it's denoted like this. And okay, so go to general graphs now. If we are given a general graph with a set of vertices v and edges e, and some failure probability p, we may ask ourselves what the reliability of such a graph is. And just reasoning like we did with the pentagon, we see that this graph stays connected whenever there is a spanning connected subset of edges that stays connected. So we do just the similar thing we did before, and we get the following expression for the reliability. So we sum over all spanning connected subsets of the graph. And the summand is then the probability that each such subset is connected. Okay, so for a fixed graph G now, if we keep the probability p as a variable, then this expression is a polynomial in p. So this is a graph polynomial. And in fact, it's a restriction of the famous Taut polynomial. It's a very well-studied polynomial in graph theory. And for a given graph G, the Taut polynomial has two variables, x and y. And if you plug in values for x and y and evaluate the polynomial at those values, then what you get is usually the answer to some counting problem concerning the input graph. So, for example, if we plug in x equal to 1 and y equal to 1, then the Taut polynomial evaluates to the number of spanning trees of the graph. And if we restrict y to be 0, then the Taut polynomial reduces to the chromatic polynomial. So along this line here, for certain integer points, evaluating the Taut polynomial at those points gives the number of proper k colorings for whatever point k we are at. And if we restrict to certain hyperbolas in the plane, x minus 1 times y minus 1 equal to q, then what we get is something called the Q-state Potts model from statistical mechanics. So that's a very well-studied model in the physics community. And yeah, not maybe very visible, but from the line then from x equal to 1 and with y above 1, on that line the Taut polynomial reduces to the reliability polynomial. So in that case, the failure probability is 1 divided by y. Okay, now you may have noticed in the Taut plane that some of those problems were NP complete, and some problems like counting the spanning trees is polynomial time solvable. So we see that the complexity of computing the Taut polynomial at various points may vary drastically. So we ask ourselves what the situation is for the reliability polynomial. So for a fixed probability p, how hard is it to compute the reliability in terms of the size of the input graph? And here we can, of course, either talk about the number of vertices or the number of edges. Okay, so let's go back here again. We can see that this is a sum over edge subsets. So a straightforward summation here is edge exponential. So then we can ask ourselves, is there some trick we can use to get the complexity down a bit? So first looking at general graphs or multi-graphs where we allow multiple edges in loops. Then Buzzacott showed in 1980 that, yeah, we can be a little bit more clever and get down from edge exponential to vertex exponential. He gave an algorithm for that. And then if we restrict to certain graph classes like planar graphs, for the case of planar graphs, Cecchini, Maintani showed in 95 that the situation there is much better. Then you can actually get down to exponential in the square root of the number of vertices. So, and then there have been a couple of improvements on Buzzacott's result. Slight improvements, but all of them are still vertex exponential. So we ask ourselves, is this optimal? Are there some lower bounds maybe that could help us answer this question? And not much was known about this until recently. So first we need the introduction of the exponential time hypothesis. And you have already seen a quite detailed formulation of that. Basically, it says that solving 3-SAT requires time exponential in the number of variables. Okay, and then earlier this year, Del, Husfeldt, and Wallin introduced the counting version of the exponential time hypothesis. And it's exactly what you expect it to be. The counting version, you just add some counting stuff, and you get the counting version. And note that this is a weaker hypothesis, because clearly counting the solutions must be a more difficult problem than just deciding the formula. So if you don't believe in ETH, maybe you could still believe that this is true. Okay, and they needed the counting version, of course, because we are dealing here with counting problems. So now equipped with counting ETH, Del, Husfeldt, and Wallin showed earlier this year that that Buzzacott's algorithm here was in some sense optimal. There is a lower bound exponential in the number of vertices. Okay, so now what we have done in this paper is we thought that for most of the interesting applications of graph reliability, multi-graphs are not really interesting. What we have is simple graphs. We don't need multiple edges or loops or anything like that. So we look at simple graphs, like this one. And what we show is that there is a lower bound exponential in n divided by log squared n. So we lose a polylogarithmic factor from the lower bound up there. But still, this is enough to establish a gap to the planar case. So we see that for simple graphs, it's still not as, for general simple graphs, we're not in the situation we're in with planar graphs, so we can't hope for that kind of algorithm. And also this polylogarithmic factor loss is somehow inherent in our reduction, so maybe could also rid of that eventually. Yes, okay, so now let's look at this result from a Taut perspective. So we go back to the Taut plane, and we want to know what's the exponential time complexity for general Taut computation for simple graphs. And in 1990, the picture of the complexity landscape of this plane looked something like this. So Jager, Vertigan, and Welsh, they showed that for certain points here, the yellow points, for special points in a certain hyperbola, their computing Taut polynomial for simple graphs is polynomial time solvable. And for the rest of the plane, it's number p hard. So in a sense, they completely mapped the complexity of the problem. But of course, then equipped with number ETH, we could get a more detailed picture of the landscape. So from Del Husfeldt-Wallén paper, we now know that the x-axis here, the chromatic polynomial, has a lower bound exponential in the number of vertices. Some blue lines here were left open. They were a bit difficult to analyze. And the rest of the Taut plane had a lower bound exponential in n divided by log cube n. So in this setting, the contribution of this paper was just to fill this gap here. So we just closed the reliability line and showed that it had a lower bound of n divided by log squared n. And then, yeah, so this is what's in the proceedings. And then now, just a couple of weeks ago, Holger and myself looked at this again and were actually able to show that, for example, if you look at the extended reliability line, like all the way down here, then we can, from a certain point on here and downwards, we can get the same lower bound also. So we have mapped that part also. Then we have an annoying part in the middle that we are working on. And yeah, okay. These two blue lines, the y-axis and the line here beside that one, we could just merge into these complexity results. And finally, this open hyperbola here, we saw had a lower bound of n divided by log to the 4n. So it's off by yet another log factor. But so this means there is not a lot of open lines left in the plane now. There is this strange line that seems our methods doesn't really apply here. The line where y is equal to 1, I think it corresponds to counting weighted spanning forests of the graph. So that's an open problem still. And yeah, so that's the state of affairs currently, and now we can have lunch.
Other questions? If not, then let's thank Nina and all speakers of IPAC again. Venkatesh has some concluding remarks.
Yeah, not lunch yet. 5 more minutes.
How do you?
So we hope that you enjoyed the symposium. If you did, the credit should go to a lot of people. So we first thank all the invited speakers, Feder Foreman, Anuj Dewar, and Toby Walsh, who gave very inspiring talks on multiple areas in parameterized complexity. Thank the program committee for ensuring that we had an excellent program. Also the external reviewers, the speakers, the authors, the chairs of the sessions. Despite the cancellation, we are stuck to the time. All the participants, the sponsors, as I mentioned in the business meeting, all of you, the registration was the major income. IMSC and France for sponsoring the Excellent Student Paper Award. Also the Indo-German Max Planck Center for Computer Science for sponsoring the pre-IPEC school. Okay, so these are the people behind the scene, the organizing committee chaired by Meena, who's there. Vikram Sharma, Narayan Kumar, Ramanujam, Saket Saurabh, and Vikram Sharma, they're all here. and several others, everyone in the computer science group of IMSC page 10. Special mention, Kamal, who's been running around making sure the vehicles leave on time. He didn't have control on arriving on time, but Neil Dara and Philip on website registration, these two people really rescued the technically disadvantaged program committee chairs. Saket would say that whenever there was a problem with the website or the registration, they were there to rescue us. Radhesham, who wrote the registration code development, and the team under Soumya, who's been very efficient in ensuring that your mics work and your talks are loaded in the laptop on time. The administration, accounts, technical maintenance, housekeeping, catering staff at IMSC. Finally, the party is not over yet. FSTTCS starts this afternoon. In fact, the first contributed session on FSTTCS is on parameterized complexity. So don't plan your shopping trip yet. And those who are leaving after IPEC, have a safe trip back, and see you next year at Saarbrücken. Given the number of events that happen in parameterized complexity, we probably will bump into each other even before. Okay. Thank you.
Ladies and gentlemen, it gives me great pleasure to welcome you all to the 30th FSTTCS conference, which begins now and will continue till Saturday afternoon. I hope all of you will enjoy the conference. Meena and I are really want to welcome you here. If you have any difficulties, please excuse us, but please do tell us so that we can help you out. The people who have these badges with the red spot are locals, and you can ask them for any help that you require. There is a transport schedule and so on put up outside, so please take a look at that. Please take a look at the events. Some of the events were there already put up. They'll be again put up at the tea break. Okay. So as our first invited speaker, we have Professor Viesau Zilonka. He's from l'IAFA in Paris. He did his PhD in the Technical University of Warsaw in Poland, and after that he moved to France. He was at University of Bordeaux, where I saw him for the first time, and he's now in Paris. He's also worked in a wide variety of areas. I mean, when I first heard of his work, it was about Zilonka's theorem, which is a famous theorem about automata, concurrent automata, which he called as asynchronous automata. And then he worked in distributed algorithms, and now he's more in the area of games. And he's going to tell us today about moving from multiplayer, two-player games to multi-armed bandits.
So thank you very much for the presentation, and thank you very much for the invitation. And well, in fact, if I work on games, it comes from automata, because some time ago, maybe 15 years ago, I tried to understand Rabin's theorem, and roughly speaking, I failed, and this motivated my work on games, and which developed now in different directions. And so I will try to explain some recent work, which is partly published, partly not published, and some parts are not new, even if they are not published, because some results, which are common results that I get with my student, ex-student, Hugo Gembert. So we we had hard time just to write it correctly, not correctly from the mathematical point of view, because it's, well, but correctly in the sense that to formulate in such a way that, that we can put inside all the different cases that we can conceive and consider and so on. And this was a hard point and and only very recently we found a way to formulate it in the most generic way. But I will not try to do it now because I do not try to make my talk too abstract. So I will be much more concrete, and only in the end I will try to explain what should be done and what should I say instead of what I am presenting here to cover all interesting cases and what everything, what everybody would like to know or to examine, to investigate. So I will speak about the games, but also the framework will be very particular because this is not the most general framework, but well, this can not be the most general framework because the framework is general, so you have the theorems that are weak, and so we should restrict the framework. Otherwise the theorems are maybe interesting for mathematicians, but not maybe so interesting for computer scientists. Because we are interested in not only interested in a way how the games are solved and how we should play optimally, and we are interested in some classes of strategies and not in all possible strategies. And in mathematics, especially if this is mathematics used in economics, they are not really interested even in strategies, because what is interesting for them is the equilibria. And how they arrive to this equilibria, apparently is just secondary for them. The real point is the equilibria and not the way to arrive to them. So the framework, this particular framework, will be described by arenas. What is an arena? So we have, like in automaton, so we have a finite number of states. So I will only consider finite arenas. So there is a finite number of states, finite number of actions. I will talk about probabilistic games. So there is the transition function is like in probabilistic automata. So if we have a triple state action and the next state, so this mapping delta gives the probability. This is the probability of arriving at this second state if an action is executed in this first state. So this is like in probabilistic automata, and there are two players. So there is a mapping which assigns to each state the player who plays at this state. So now you can see the dynamics. At the beginning, the game is at some state. So the players controlling this state chooses an action. The nature chooses the next state because the nature uses the probability to, and this transition mapping to choose the next state, and the next player, or maybe the same, it depends who controls the next state, chooses an action, and this continues. I suppose that at each state there is a non-empty set of available actions, so the game never stops, and we have a kind of an infinite path in this structure, and well, so we can make pictures like for automata. So we have here one state, another state, and Square is, this means that this is controlled by one player, and circle, this is controlled by another player, never mind which one here. And the transitions are labeled by the action and the probability. This is the probability of going to T if A is executed at S. And this is true probability in the sense that normally the sums of probabilities of outgoing edges for a given action should give 1 if the action is available and 0 if the action is not available at this state. And so this is a small example of arena, and we have here, for example, if we consider this state, so if we take the action D, so with probability 1/2 we can go here, and with probability 1/2 we can go here, and so on. So we change the states, and the game is played in this way. What is of interest, now the players, well, they should use some method to play, and they do not know the future, so how they play can depend on the past, but not on the future. And this gives us the notion of strategy. So a strategy for a given player is a mapping, which gives here. There are only 3 buttons here, but 3 is too much for me. So so here we have a strategy for one player. And what is a strategy? So here is a finite sequence of states and actions terminated here in a state controlled by player max. We have 2 players, max and min. And this gives a distribution over actions available at this last state. Because the players are not obliged to choose just one action, they can use the distribution over available actions at the last state. And so here this prefix is the finite past up to the given moment, and here we have the current state, and here we should have a distribution of actions, of available actions. Well, strategies are complicated objects, so well, in mathematics they don't care if this is complicated, because they just use them like that, and these are abstract mathematical objects. But for us it's important, and maybe important, to have simpler strategies. And a simpler strategy is a strategy which is memoryless and deterministic. What does it mean, memoryless? Memoryless means that the strategy does not depend on the history. So it depends only on the current state, and deterministic, that the strategy does not use the probability distribution to choose an action, but just fixes one available action for each given state. So this simple strategy is just a mapping from states to available actions, where here delta of S, this is my notation here, this is the set of actions that are available at S. Well, this is a restriction because even if we do not like complicated strategies, we can try use the strategies which are not complicated, but just finite memory strategies, when maybe we do not remember all the past, but we have some finite memory which is updated with each move. This is of course sufficient to implement in a computer way such a strategy. I limit myself here to memoryless deterministic strategies because, well, allowing more general strategies with memory. So this is something which should be done, but this is not done only for some very specific games. We have some results in this case. So I limit for this reason, for the reasons which are not related to computer science, but related rather what I can do and what I cannot do. I limit myself to more or less deterministic strategy. Well, here we have games which are, so this is a probabilistic process now, because we have the arenas where the probability is incorporated inside. So formally, we are not obliged, but it is very convenient to use usual mathematical notation of random variables and so on and so on. It is possible to do everything without it, but it's not a good way, because finally at some moment you see that it's impossible to do it without proper notation. It's not pure hazard that probabilists use some notation, because this is the notation that proved to be efficient. So I should do it here also, but it's not. I will not suppose that everybody knows this probabilistic mechanism and theory of stochastic processes and so on. So my notation is very, very limited. But formally, we have here stochastic processes, and this is the first process which gives the action taken at stage I. So we have infinite number of stages. And so the values, the AI gives the action taken at stage I, and SI is the state at stage I. And next, this is a difficult, a complicated notation, just to say a very simple thing. It says two things. Here we have an initial state S, so we fix some initial state. We fix here a strategy for the first player, for player max. Tau is the second strategy. This is the strategy for the second player. And if we fix the initial state and the strategies of both players, so from the point of view of probability, it fixes completely the probability space and the probability measure. And intuitively, it's rather evident. The first thing here says simply that if the initial state is S, so the state at the first stage with probability 1 should be S, which is evident. The second equation just says that if we take an action at stage N, so with this action is given by the strategy of the player acting as this state. So here, if the last state is controlled by player max, so we take the strategy of this player, so this depends on this finite history in general, and this gives the probability of executing this action AN after this history. If the last state is controlled by player min, so we have here the probability of executing this action according to strategy of player min. And the last equation just says that the state taken at the stage n+1 is determined completely by the structure of the arena. So this is given by the transition probability. So if we have some history, finite history, here is the last action. So what is the probability to go to this state? This is just the probability to go from this last state to the state S plus 1 by executing this last action, an. This is nothing, this is just a long notation for a simple thing, and in this way, we obtain, the probability space is in fact the space of all infinite sequences of states and actions, and like always in probability, we should have some algebra of events, and here in natural way we take Borel algebra, but well, we should not care about this point. What is important is that from this equation we get only one possibility to define the probability measure over this infinite sequences. But, well, this is just to say that everything is well defined, but I will not really use these definitions later. So we have now two players, I call them max and min, and now the question is what is their aim? What they want. And I will here suppose that we have the following setting. This is the usual setting used for this kind of games. I will explain later that maybe we should do something with this setting. And this setting is that, well, we have a mapping. This is payoff mapping. So here we have a set of infinite sequences, infinite histories. So we have this infinite play, this gives an infinite history, and this mapping gives for each infinite history a real number. This is the payoff received by player max, and this payoff is paid by player min. So the objective of max is to maximize the payoff that he receives, and the objective of player min is to minimize this payoff. So we should have some mathematical assumption in order that these things should be well defined, so the function should be measurable and so on and so on. But again, this is not maybe very important for us here. So a game is here a pair of arena and of payoff mapping. I use the letter U because in game theory people sometimes speak not about payoff mapping but about the utility mapping. So utility is the first letter of U, but well, I will call it payoff mapping. And now I can define what does it mean that player what is it an optimal strategy? What is it an optimal strategy for player max and for player min? So we have these two players, but the environment is probabilistic. So of course, the result of each play is just infinite sequence, but at the beginning, we do not know what will happen even if we fix strategies, because the environment also makes some choices. So formally, it means that we should look at the expectation of the payoff. And so what player max wants is, in fact, he wants to maximize not the payoff, but rather the expectation of the payoff. And the player min wants to minimize the expectation of the payoff. And now optimal strategies. So we say that sigma sharp, tau sharp are optimal if we have the following inequality. Here we have a real number which is called the value of the game for a fixed given initial state S. Here what happens? Here this inequality says that if player max uses his optimal strategy and player min uses some other strategy, any strategy possible, then the payoff, expected payoff received by max is at least the value of the game at this state. This inequality says that if player min uses the optimal strategy and player max uses any strategy, the payoff cannot be greater than the value of the game. From these inequalities, if we put inside, if we put inside tau sharp and sigma sharp, we see that if both use the optimal strategies, then the payoff is exactly the value. And we see also that they have no interest to switch to another strategy, because we see that here, if player min tried another strategy, then his loss is at least as great as the value of the game. And here, player max tried another strategy, and what he wins cannot be greater than the value. So this inequality says that when we have optimal strategies, that this is a kind of equilibrium, and nobody has interest to change this, to change his strategy, and to use a strategy which is not optimal. And now the basic question that I will consider here is what is the situation, in what kind of games both players can have optimal strategies that are both deterministic and memoryless? So in other way, in what kind of games both players have simple optimal strategies? So I will begin with some simple games, and the simplest possible game is a game with only one player. Already a game with one player can be very complicated, because well, there is games with one player. In this type of games with one player are known as Markov decision processes, and there is a theory well developed of Markov decision processes. So this is not trivial to consider games with one player. And in fact, I will show that in fact, the difficulty is. The great difficulty is to understand the games where there is only one player. If we understand the games with one player, then at least if we just consider the question if there exist simple optimal strategies, the passage from one player to two players is something automatic. And for one player, we do not have really general criteria. We have some partial results, which now are quite interesting. So this is not the results that we can apply just to one game or two games. They are quite general, but on the other hand, we have some limitations which are very serious. The first limitation concerns the utility mapping, the payoff mapping. So for a moment, I will suppose that the payoff mapping does not depend on the finite prefix. So the payoff depends, how to say, what happens at infinity. And formally, this is the definition. So it says simply that, if we have some infinite history and if we cut a finite prefix, this does not change the payoff. Maybe to motivate, I will give two examples of payoff which are prefix independent. The first example is well known, used in mathematics. These are mean payoff games, but I just modified slightly to other some new ingredient to mean payoff games. So here we begin with two functions. The first function is the reward function. So this gives a real reward for each action. And the second function gives a positive real number for each action. This can be seen as a kind of duration of the action, intuitively. And what is a mean payoff? Well, mean payoff over first n stages is given by this formula. So what we have here, we can see that this is the reward at stage I multiplied by the weight of this stage, and we take the sum of these terms, and here we have just the sum of the weights. And so if we interpret that the weight is just the length, the time length of the action, and R is the reward by time unit. So this is the mean reward by time unit, intuitively, over the first n stages. And we go to infinity. There is a small mathematical problem that maybe the limit does not exist, so I will take here the upper limit supremum of these expressions. And so this payoff does not depend on a finite prefix. So you can cut a finite prefix. This does not change the limit here. So this is the first typical example. And another that some people like from computer science. So there are parity games where here we have a kind of, we have a priority mapping, which gives here a positive integer for each action. And now the payoff is the smallest priority visited infinitely often. This is the priority of the infinite path. And the payoff is this smallest priority visited infinitely often taken modulo 2. So this payoff is either 0 or 1, depending on the parity of this priority visited infinitely often. So again, because what is interesting is the priorities that are visited infinitely often, it's clear that this does not depend on a finite prefix. And for this type of payoffs, so payoffs that do not depend on a finite prefix, Hugo Gembert found a few years ago a criterion which is quite powerful, which says when such games have optimal simple strategies, games here with one player, only player max. So we have here only player max, there is no adversary, he should maximize the expected payoff, and we suppose that the payoff does not depend on the finite prefix. And he found that if the payoff satisfies the following inequality, then the unique player has an optimal simple strategy. And this inequality, what does it say? It says that if we have two infinite words, and if we take a shuffle, then the payoff of the shuffle is not greater than the maximal payoff for these two words. So intuitively it means that it is not useful to interleave two infinite words. One of these words is always better than this interleaving. Well, there are two things which are remarkable about this theorem. The first thing is that it works. It is remarkable that it works because we have a probabilistic environment and we have a criterion where there is no probability at all. So I was very surprised by this result because roughly speaking, I never believed that we can find something like that, a characterization like that, which can be true and which can be applied, because of course we can have some conditions which are maybe true, but we cannot maybe find an interesting game which satisfies this condition. What is remarkable that, for example, this condition is satisfied by these two previous games, by parity game and by mean payoff game with limit superior, with upper limit. So, so this shows that these two games, when there is one player, this unique player, maximizer, have a simple optimal strategy. And this is not totally trivial, especially if we consider mean payoff games, because, I know only one proof that I can understand that works for mean payoff games that shows this thing. Because roughly speaking, what mathematicians consider in for mean payoff games is not exactly what I put here, because well, here you can see that I consider the expectation of the payoff. And what mathematicians consider when they speak about mean payoff games, that they put the expectation here and they take a limit superior of the expectation, which is quite different than putting expectation here before limit superior. This makes these two games which look very similar, in fact very, very different. And if you put the expectation here inside, it becomes much simpler to demonstrate that there is a simple optimal strategy. And if you put, roughly speaking, if you put the integral outside, it's much more difficult. And there is one proof made maybe 10 years ago for this particular kind of games. So, so this is not so trivial. But as I said, well, so the criterion is really surprising for two reasons. That it is true, but there is no probability inside. And there are some real interesting payoffs that satisfy this criterion. But there are also interesting payoffs that do not satisfy this criterion. And what is amusing that if you switch and instead of upper limit, you take a lower limit here, it looks, well, very similar, but so this is mean payoff. The weight is just 1 for each action. But this payoff does not satisfy this criterion. So using you cannot just apply this criterion to prove that the games with this payoff admit simpler optimal strategies. So of course you can prove it in another way because and so on, but well, not by directly applying this criterion. So there are some limitations, and there are some, now we know that there are some other payoffs that are interesting and which do not satisfy this criterion of Hugo-Gember. So I will try to give another criterion which is more probability-oriented. And I will begin with some very simple games. And the very simple game is a game without players, which means that there is only one available action at each state. So we have just a Markov chain with a finite number of states. So let us suppose that here we have this Markov chain. So I will not give here the probabilities, but you can imagine that the probabilities are such that the sum of probabilities for outgoing edges for a given state is just 1. There is only one action, and well. And now we can decompose this Markov chain. So we have here transient states. So the states that you will never state, even if you begin here in this part, you cannot stay in this part forever. At some moment, you are obliged to go either here or here. So here we have the set of transient states. And since our payoff does not depend on the prefix, in fact, what happens here is not important, because the payoff does not depend on this part. What is important is what happens here. So this is one recurrent class. So all states here are connected, and all states here, if we go here, all states here will be visited infinitely often. And here is another recurrent class. And what is interesting, in fact, is what happens in such part, and this part, and in this part. And it turns out that if payoff does not depend on the prefix, the situation is very simple, because in each such component, the payoff with probability 1 is constant. So, of course, for different histories, you can have different payoffs, but with probability 1, all these payoffs are constant, so the other payoffs appear only on paths that, in fact, you will never take. And now we should go to the case when we have really one player. And when we have one player, it can be useful to understand what happens if we have what happens in the deterministic case. So there are no probabilities. If we take an action, then with probability 1, we go to the next state. So like in finite automaton, the payoff does not depend on the finite prefix. And what we can do, so we can have a stack and put the actions on the stack. And when we have a cycle, then we cancel this cycle. And we can see that, well, there is some number of actions that will be not canceled. They are at the bottom of the stack, and they are there forever. And next they are cycles that we cancel, and so on. And since our payoff does not depend on the prefix, it's clear intuitively that if we have a payoff such that the payoff over, that there exists a cycle such that the payoff over the cycle is greater or equal than the payoff over the path, then our best strategy is just to take this cycle. Now, the question is, when we go from the deterministic case to Markov decision process, it does not make really sense to consider cycles. Cycles, if we fix a cycle, we cannot repeat this cycle infinitely often. This gives a path which has probability 0, so it's not very interesting. So the first question is, if we have Markov decision processes, then instead of cycles, what we should consider? And how we obtain cycles? If we have a deterministic game, if we fix a simple strategy, simply it means deterministic more or less, then if we start at some point, we will go, after sometimes we will go and repeat a cycle. This is like a finite automaton, which just we fix one action for each state, so we have just, after some moment, we go to the cycle and we repeat this cycle forever. Now, if we have this Markov decision process, if we fix a simple strategy for our player Max. Deterministic memoryless, what we get? We fix a strategy, we get a Markov chain. We get a Markov chain, and instead of a cycle, what we get at the end, we get a recurrent class, which is repeated, where there are states that are repeated infinitely often. So now this recurrent class replaces a cycle. And previously, we did some decomposition of an infinite path in cycles. Now we should do the same thing, well, nearly the same. It's not exactly the same, but we should make a decomposition of, but not in cycles, but in pieces that belong to Markov chains. So we make some kind of decomposition in Markov chains. I will try to explain it later. And what we get in the end is what is known as multi-armed bandit. What is multi-armed bandit? Each arm is just a Markov chain. So we have here 4 Markov chains. And so these are 4 arms. And there is one player. And at each stage, he should choose one arm. He pushes a lever, and so he goes to the next stage in this Markov process, and the next stage he chooses maybe the same, maybe another process, and he repeats these things again and again. This is multi-armed bandit. Multi-armed bandits are well known, there is a theory, but the theory for multi-armed bandits was developed mainly for some special kind of payoff. This is discount payoff, and this is not a payoff. This is a payoff that heavily depends on the finite prefix. So this is not exactly what we need here. So we are interested, in fact, this finite components. So not each Markov chain is interesting for us. Only Markov chains that are irreducible. So there is only one class where each state communicates with each other state. So these are Markov chains which are of interest here, because our payoff does not depend on the prefix. And the question also changes, because now my question is, I do not ask, so here what is a simple strategy? Previously, simple strategy was a strategy that depended on the state. Here I said that a strategy is simple if this strategy chooses just one arm each time. So in this context, simple strategy is a strategy that chooses one arm at each stage. And the question now is when, for this multi-armed bandit, when simple strategies exist, optimal simple strategies exist. We can see that the problem, there are simple strategies for the payoffs that we considered previously. So for mean payoff, if we have many arms, all arms irreducible Markov chains, so the best play is just to take the arm which gives the greatest payoff. It's no interest to interleave these things. For parity, it is evident, because for parity, if we have several Markov chains, so either there exists a Markov chain which is good for parity game, so we should play always in this chain. So either there is no chain which is good for parity game, so always we can choose one chain and play in this chain, because in any way we win 0. So it's not important. And what happens is that, well, now I will try to make a link between these two problems. So simplest strategies for Markov decision processes and simplest strategies for multi-armed bandit problem. But you should remember that simple does not mean the same thing in both cases. So I will define a subarena. What is a subarena? The intuition is simpler. We just remove some states and some actions, but what is left should be an arena. So this is a subarena. If we have a Markov decision process, so we can extract some subarenas which are Markov chains. Just we limit for each state, we just take one action. Okay, there are many possibilities to do it, of course. So there are many chains that we can extract from each arena. And not only we can extract many chains from a given arena, but also we can extract several times the same chain because maybe they are not, we can extract the chain, but we should also indicate which is the state of the chain. So if we extract a chain, we should choose the state, and maybe we have the same chain, but the state not is the same. So this is like two different chains. And now the main result is that if we take a Markov decision process, so one-player game. And now we consider all multi-armed bandits that we can obtain from this chain by extracting the Markov chains that are inside. There is an infinite number, of course, of such multi-armed bandits. But if we are able to prove that for each such multi-armed bandit, there exists a simple optimal strategy that chooses just the same bandit at each stage, then there is a simple optimal strategy in the initial game, one-player game. So this makes a link between these games, these different games, and this gives a condition which is, well, more probability-oriented because we have one probabilistic game and we reduce the problem of the existence of simple optimal strategies to another simpler game with, we ask another question, roughly speaking like that. And for example, now we avoid some problems that we can have with the criterion invented by Hugo Gembert, because now the problem with the lower limit disappears for the simple reason that if we have a Markov chain, so with probability 1, there exists a limit. So upper limit or lower limit, it does not matter because with probability 1, there is a limit. This was a kind of weak point in the criterion of Hugo Gembert because he asked, his condition requires something for all histories, but some histories appear with probability 0, and for these histories, we do not care if they satisfy this criterion or not, and so on and so on. So this avoids these problems. Now, from one player to two players, it appears the situation is much simpler. First of all, I do not suppose now that, that the payoff is prefix independent. This can be any measurable payoff. And to formulate, and I would like to reduce the problem from two-player games to the games with one player. And the reduction is the following one. First, I define what does it mean, a morphism of arenas, but the intuition is, well, the definition is too long to read, so I will give it with the picture. What is a morphism? The intuition is simpler. You have here one arena, here well, one transition of another arena. What is it, the morphism? Like in automata theory, if I have here a state S1, and by the morphism is a mapping from states to states. So if this morphism maps this state to S, this state to T, and if there is a transition here labeled by A with a given probability, transition probability, so here I should have also a transition labeled with the same state and with the same probability. This is just a definition of morphism. It's like morphism for automata, but just you should see that this is double labeling, because actions are labeled not only by the action name, but also by the probability. And the morphism should preserve the actions and the probabilities. I will call the degree of the morphism the maximum number of states or in the inverse image of one state. So for each state, well, if I return here, so here say that for this state, the inverse image is only this one state. For this state, we have in the inverse image two states, and if this is the maximum, so the degree of the morphism is 2. It's just maximum number of vertices in the inverse image for the states. So it's the first thing is that given an arena, there is an infinite number of arenas which we can such that there exists a morphism from this upper arena to this arena which is on the bottom. But if we limit the degree of the morphism, the number of arenas here is limited. So for a given arena, we have only a limited number of arenas such that there is a morphism of degree at most 2 and so on and so on. If we consider what happens if we look at these arenas from the point of view of game theory, and if we have here one arena, another arena, and the morphism. If we have here an infinite path, so we fix here in the initial state, we take an inverse morphism. In the inverse morphism, you can have several states, but let us choose one of them. So if we choose here one state, one initial state, so there is only one path here which can be mapped to this infinite path. So there is a correspondence between this infinite path, and if we suppose that the payoff for the paths that are similar is the same, so the games are not different from the point of view of the players. What a player can do here, he can do here, and vice versa. So this is like the same plane, the same games. It's like a by simulation, say, or something like this, in fact. We can even systematically construct all possible morphisms. It is like the same construction which can be done in graph theory for covering of graphs. It's very similar. And next, I will need again one definition. Well, I consider two-player games, And now I will consider subarenas. If I consider subarenas, so I remove some actions. And if I remove the action in such a way that for one player, say min, for each state controlled by min, there is only one possible action. So in fact, this player min in this subarena has no choice. So this is like a one-player game, okay? And now we have the following result. So again, this is a kind of reduction of the problem if there exist simple optimal strategies for two-player games to the same problem for one-player games. So I take a two-player game. I take all arenas such that there exists a morphism from these arenas to my arena. And I can consider only the morphism of degree 2. It's sufficient. So I take all these arenas. This gives a bunch of two-player games. And now I restrict the moves of one player in such a way that I have a one-player game. So I remove the possibilities for the other player. This gives me a bunch of one-player games played on another arena because I am on this upper arena. Okay, so and from this upper arena I removed some actions. So I obtain a bunch of one-player games. And we can prove that if for all these one-player games we have simple optimal strategies, then we have simple optimal strategies for both players in the initial game. And well, in fact, this is rather a theorem that says something about the game because, in fact, this can be applied even for the payoffs that maybe you need some memory for another arena, because this depends really on arena. Okay, because we have one game and we have a condition for one fixed game. But of course, next we use this for the class of arenas. So if we have, for example, parity games, if we do this process, so we obtain one-player parity games. And for one-player parity games, it's evident that there is optimal memory-less deterministic strategies for this unique player, either min or max, because we should consider both cases. And this is sufficient to prove that there exists optimal memory-less deterministic strategy for all two-player games. And we can do this with any payoff. And this maybe explains why this is a remark which is kind of a trivial remark, but which was observed by many people that they observed that, well, mean payoff games, for example, parity games seems to be very different, but they observed that, in fact, the algorithms used, the methods used to prove that there exist optimal memory-less deterministic strategies very often are the same. So why this is true? Well, I think that this is this explains this phenomenon because, in fact, if games are similar as one-player games, it means that to go one step higher and consider two-player games, nothing can change. So it explains that this apparent similarity between different proofs and so on and so on. So the ingredients of this existed before. And in the end, just to say one thing, well, I spoke about games with payoffs. But there are many games where the payoff seems not to be very adequate. And if you consider why we need payoff, in fact, a payoff is just a real number. Why we need a real number? Just to compare two real numbers to say what is better than other. If we speak about optimal strategies, so the value of this real number is not very important. The order is important. If we do not have optimal strategies, but only epsilon optimal strategies that approach the value of the game, the exact real number is important because you should say what does it mean, this epsilon, what does it mean to be small. But for optimality, it's not important what does it mean to be small. And well, I will give you two examples. The first example is taken from a book of game theory of Osborne and Rubinstein. It's well-known textbook on game theory. They consider only deterministic games, so we have only infinite paths, no probability at all. And we should compare, and they have a method. They use this method to compare infinite paths. So here we have an infinite sequence of real numbers. So you imagine the states are labeled, or actions are labeled by real numbers, and after infinite play, we get an infinite sequence of real numbers. Here we have another sequence, and now we can say what does it mean that this sequence is better than this sequence. And this is the criterion which says that, well, you consider the sum of the payoffs over first n stages. And if there is a moment where for the first infinite sequence, this sum is always better than for the other sequence, then intuitively the first sequence is better than the other, because if your payoff is just the sum of the day payoffs at each stage, so it's clear that you will prefer an infinite sequence where after some moments you are always better than for the other sequence. But now, well, if you try to explain this, to put it using payoff mapping, so you can try to make a payoff mapping which maps each infinite sequence of real numbers to a real number in such a way that we get the same order. In principle, it is possible. It is possible by cardinality arguments. But to find explicitly such a mapping, I don't know how to do it. So what is possible, it does not mean that you can always realize it, and this is not useful. So what is important is the order. Now you go to the probabilistic case, and roughly speaking, we can find the same thing. So what is important? Well, why we use real numbers is to take expectation. And why we take expectation? Because we know how to calculate what is an integral. Roughly speaking, this is what happens. But in fact, this is not so important. What is important is something else. As I said, if we fix strategies for both players and initial state, we have a probability measure. And in fact, if we take a utility mapping, a payoff, this is in fact to compare these different measures, because we say that one measure is better if one integral is better than the other. But we do not need integrals for this. What we need is an order relation over measures. So if we have an order relation over measures, this is all what we need to define what does it mean to have optimal strategies, and it is all what we need to prove all these theorems, in fact. Now, the question is if it is useful. Well, at first you can say that, well, it's not so evident because what does it mean, compare measures, and so on and so on. But next you look, even in Markov decision processes, and even in Markov decision processes, you can have a situation, what is called a semi-Markov decision process, where, roughly speaking, if we have a state and an action, it does not give, for example, directly a reward. It gives some probabilistic event. So here we have a situation where state and action does not give a reward, but some probability distribution over rewards. Nature chooses reward from some fixed probability distribution. The nature chooses the weight from some fixed probability distribution, which depends on the state and action. And next, you can define what does it mean. Payoff? But now payoff is really a random variable, and so on and so on. But you do not have the payoff, a payoff now for each infinite history. For each infinite history, you have a kind of distribution over some abstract events, and so on and so on. And in fact, this type of games enters in the framework of comparing probabilities rather than expectations. So really comparing probabilities rather than comparing expectations can be useful. And it is useful because even if somebody does not like semi-Markov decision process, and it happens that sometimes you need semi-Markov decision processes, because even if you like not only probabilistic games in the sense defined previously, there are some results that you cannot prove in this framework. You should take this larger framework of semi-Markov processes, and so on and so on. It's like in mathematics, sometimes it's easier to prove some things if you have a framework which is more general and larger than the initial framework. So this is something really useful, and it is always useful for deterministic games, as I tried to explain previously. So the real point is also that maybe we should more focus attention on this order than on the payoff. And if you look, the inspiration is taken from this book of Osborne Rubinstein. They considered only deterministic games, but you look at their book, that they never speak about payoffs. They speak about they compare infinite sequences and so on. They speak about order and never about payoff. So everything is possible to do is in this framework. Thank you.
Questions, comments? Yeah.
What about finite memory strategies?
So, I cannot. I don't know much about finite memory strategy because, well, first of all, the problem with finite memory strategy, there is a great problem with this kind of reasoning like here, because at the beginning, we have very few examples of concrete. And it's very difficult to make some general theory if you do not have examples. This was our first problem here. And for finite memory games, well, you have rabbit games, street games. Now you have some other games, but well, it's really difficult to generalize, because it's difficult to test your hypothesis if you do not have examples. There is another question which is maybe more pertinent, because the other problem is that normally, so it depends what is the aim for what is the aim for you to use how to use the games. Roughly speaking, if you use the games to do something in automata theory, then really you should have two players that have a finite memory strategies. But for verification, roughly speaking, what you need is one player who has finite memory strategy. This is our system, but the other players, this is the nature, and the nature, well, we don't care. So the question, more interesting question is, can we do something, some theory, or identify some general criteria for the games where only one player has finite memory or memoryless optimal strategies, and we do not care about the other player. And there is some work in this direction, but only for deterministic games, not in the stochastic games.
Anybody else? No? Okay, let's thank Vesau.
Thank you.